Okay, one of the ideas that we added between the .8 proposal a year ago and our .9 update in July was the concept of interfaces. This was an idea that a lot of people had asked for in different ways, and it also addresses an ongoing demand, or actually controversy in the whole old community for a number of years, which is the distinction between a type interface as a specification and a class as an implementation thing with data structure, and the desire to keep the two separate so you could actually inherit an abstract type interface without having to inherit the physical structure. And so an interface, concept is very close to this concept of abstract type. It specifies a behavior, and it doesn't specify a particular, let's say, structure and implementation. So an interface icon represents a set of operations that are supplied, and in a more complex situation, possibly an ordering in which they can be applied. That ordering could be specified as a grammar or as a state machine. But certainly the vast majority of them will simply be lists of operations that can be called. And it allows you to take some large class or class library and break it up into distinct into pieces of functionality that fit together and allow the dependencies to be made more precise. Here's an example drawn from the COM domain, in which we might have some class that supports several kinds of facilities, grammar checking, style changing, and spell checking. So the interface is drawn as a little circle. It's attached to its suppliers by solid lines. So in this case, this style agent supports these three different interfaces. And this client class is attached to the things it uses by a dotted arrow. So in this case, we're saying the client only depends on the spell checking interface of this class. And that could be, in this case, implemented by a local one or a remote one, or possibly could be implemented by an entirely different class, so that we can separate the interface that you require from which class is actually going to implement it. And so there might be several possibilities, and then clearly when you finish the design you have to say which one you will actually use. But from the point of view of the logic, it's enough to say which interface the client requires. We can also use inheritance here. Now, what does it mean with an interface? Well, in this case, it means that this interface implements all the operations from this parent interface, plus some additional operations. So it allows you to gradually extend things. And various clients would, in fact, use interfaces at different levels, depending on how much they need. So we found this captures this concept of abstract type versus class distinction. We believe it captures the distinction that's made in Java, as well as the implementation of interfaces as found in COM system. And we feel it would work for other systems as well. So I think this meets a need that many people have requested. Well, a system wouldn't be very useful if it had to be built as a monolith, as a big flat set of constructs, because you could build small things that way, but you'd never get large systems. To get large systems, you have to be able to group your model into pieces in such a way that different groups can work independently. And that means that you have to group things together that are tightly coupled. And also clearly capture the dependencies between the different parts, because they'll never be independent. If they were independent, you wouldn't have a system. So there have to be some links between them, but hopefully they're well behaved. So a package is simply a group of model elements that's treated as a work unit. It really has no semantics. Now, people sometimes get upset when I say that, but it's really a software engineering construct. It's really a configuration control unit for the benefit of people actually doing development. It's an ownership unit. It's the way you would actually package up your model into pieces. And also supplies a namespace. Now, some people would say, what do you mean it doesn't have semantics? I thought namespaces were about semantics. And I would argue that the reason why you need namespaces is because different groups are going to work in parallel and may, in fact, over time will end up accidentally using the same names in different places. The only reason you need namespaces in languages or in systems is because we're not dealing with the whole thing as one flat system. You don't need them theoretically. They're not really a semantic construct. They're a software engineering construct. And software engineering constructs exist because people don't have infinite capacity to see things, because they got to see things a little bit at a time. So I would assert that the property of being a namespace is an inherent part of being a configuration control unit, being part of a packaging unit. So a package is a unit for control, a unit for storage, a unit for naming. It's also a useful way of showing the design dependencies between the different pieces. And that's what you need to control if you're going to try and work in parallel. You can take all of the dependencies from the individual classes and promote them up to the package. So if two classes depend on each other, then the packages depend on each other. So this, the symbol we use for a package is a little manila folder symbol, just like the symbol used for directories on desktop systems, same idea. And you can nest them inside of other packages. So the entire system is a package, and it consists of other sub-packages. And they can use outside packages from libraries, for example. So this shows a model of a graphic editor, like a UML model editor, or Excel or Emacs. This model would actually cover them all. It's got several pieces in it. It's got one piece that just models the domain elements, and that doesn't depend on anything else. It's got a piece that maintains diagram elements, and that obviously depends on domain elements and whatever graphics operations we supply. And a controller ties them all together. That depends on everything, so it's not very reusable. And also we depend on outside windowing systems. Let's suppose we want to support Motif and Microsoft Windows. Well, it's a good design decision not to make the entire system dependent on that difference. We want to bundle all those dependencies in one place, and I've called that graphic core. So, if I were doing this, I would implement some kind of set of graphic operations that we use internally that don't depend on what kind of window system we got. Clearly, when you actually program it, you have to implement this twice, once for Motif, once for Windows. So I show that as actual dependencies to the specific windowing systems. And I show the fact that we have two of them using inheritance. This is the inheritance symbol, the generalization symbol. Now you might ask why we're using inheritance. That doesn't seem to make sense. But I would argue it's the exact same meaning of generalization that we have for classes. If you think about what generalization means for a class, it means that we have some general specification that the clients see, and we have more than one implementation that the client doesn't necessarily see, and that at runtime it will be one or the other, but not both at the same time. And that's what we got here. You have to write the code for both of these pieces, but at any particular system you will have one or the other actually instantiated. So using packages and dependencies of this form, you can get a good idea of the high-level architecture of your system and its dependencies. That's not everything about the architecture, but it helps you to understand whether you're getting a tangled mess of dependencies. Yes, short question.
I asked before that about the difference between, I think it was package and something else, and the answer was, okay, packages disappear at runtime. How can you have inheritance when the package concept doesn't exist at runtime?
Question is, how can you have inheritance if the package concept doesn't exist at runtime? Well, the packages represent parts of the model. I mean, at runtime, you will actually have code. Package may or may not exist at runtime. No, when you actually have a.
Let me defend this because I answered his first question.
Oh, okay. Well, Grady probably got it wrong. Hey.
Jim is right in saying that packages partition the model, but consider inheritance disappears at runtime as well too, just as it does here. The fact that I have a motif instance of a package, the fact that it comes from a windowing system, that material fact disappears at runtime, and all I see is the instance, the motif instance. Your question went back to distinguishing this versus components, by the way, whereas components are indeed runtime entities, packages only partition the model.
Now, it makes very good design sense these days to align the actual runtime code with the work boundaries, and that's exactly what a component is. It's the decision that at runtime, the code boundaries will not disappear. They will be visible, and in fact, you can actually substitute different code units at runtime. And this is very unlike the old days when if you called a mathematical library, it was gone at runtime. It was just compiled out. And if you use a database or a windowing system these days, it turns out that in fact you do see that at runtime. But you see it not because the package must exist at runtime, but because it's a very good design rule to do that, because it means that you can now make changes at runtime, and that's a good thing to do. So I'd say these don't have any inherent semantics, but whenever you draw lines, it's a good idea to draw them along logical boundaries of one form or another. Again, that's a good design principle, to subdivide your system along, for some reason. I'll take one more question, then I'll have to move on.
Are you making an analogy to the subsystem? Can a package be a subsystem, or
It depends. The question is, can a package be a subsystem? It depends on the word subsystem. We're not using the word subsystem, so in UML terms, you'll have to rephrase the question. We've stopped using the word subsystem and say everything's a package. A package is the word subsystem means about 20 different things in different disciplines. So I'd have to say, which meaning do you want? We'll look at the dictionary. And so in some uses the word yes, some uses no. Which meaning do you have in mind?
well, a discernible component of the overall system?
You have to go a little more. The word subsystem, can either be, it's sometimes used to mean, a breakdown of the code. It's sometimes used to mean something that actually exists as part of the runtime deployment. And so, a package is defined as being, a chop up of the model. The code, the pictures, whatever. I really need to move on. We'll take some more questions at the end, if you can bear with me, please. We can represent behavior in two ways. You can look from the inside out or the outside in. When you look from the inside out, you look from the point of view of one class and see how it goes through its life history and what outside events affect it. And we express that in terms of finite state machines. And they've certainly been around for a long time. We use the improvement made by David Harrell, in which he nests states inside of other states to get the exact same kind of inheritance that you get with classes. A class inside of another class, a state inside of another state is really a substate and inherits all the transitions of its parent. For example, this is the state machine for a telephone call, and it can be in different states like dialing or talking or ringing. We can call all of these the more general state called active, and if you hang up the telephone, it doesn't matter which substate you're in, it goes to the disconnected state. So that's exactly the same kind of inheritance that you get with classes. It's exactly parallel. Although, what you see, in fact, is that the notation is different. Here's a case where we found that one notation is more suitable in one domain. This is kind of a nested notation for inheritance. And with class diagrams, we use a tree-structured notation. And we found that each was more suitable to its own domain. Because in this domain, you have a lot of transition lines, and they would kind of get confusing if you use the tree notation. So we've often found that even though two things are isomorphic, one notation is better than another in a particular case. Use cases, these are the things that Ivar made very popular. They represent really a partitioning of the functionality of the system in user-meaningful terms, where a user is some outside agent that's connected to the system, either a human being, or a computer or some other system. And more precisely, it's a role played by such a outside agent. So, for example, the same human being could be a computer operator as well as a user, as well as a manager, a customer, clerk. So these are the roles that different outside objects play. And a use case is a set of interactions that's meaningful from the point of view of one of those roles. So it's a way to keep system design honest, so you don't go and design things that are neat and don't do anything. It's a way to make sure that you keep your eye on the requirements from the very beginning. So at the high level, we can show the actors in the system and the various use cases in the system. They're drawn as little ellipses, and we can connect the actors to the use cases. So if you have a bank, a customer can ask for a loan or can make some transaction at the counter. They involve different bank personnel. We can also build use cases out of other use cases. For example, in the bank situation, the customer might have to identify themselves, and that could be used as part of the description for each of these more specific use cases. Now, at that level, we haven't got much. You have to actually say how the use cases work. And to do that, you have to list the various interactions that can be done by use case. In most cases, there's not just a single set of interactions, but several possible sets. For example, if you're doing a transaction, one might be a deposit, one might be a withdrawal, but they're fairly simple variations of one another. Also, with each use case, you need to package all the error conditions that can occur, and that's very important.
There's an error on that slide. Can you use it generalization association? And this stereotype.
In any case, it's a stereotype, and it's a uses relationship. And we've decided that it's closer to generalization, but there's no mistaking it. It's a uses relationship. So to make them work, you need to specify the sequences of interactions that can occur, both normal sequences and error sequences. So to specify them, you have to map a use case to what we might call an interaction, or actually to a set of interactions. So each use case might involve a set of possible interactions, where an interaction is some sequence of messages exchanged between objects. So again, at the high level, an interaction would involve several participants. And for each one, you expand it into a series of things. Let me skip over that one. We're running a little behind. And talk about ways of specifying interactions. one way you can specify an interaction is a series of messages back and forth organized in time order. So a sequence diagram represents a way of looking at an interaction in time series. So we draw time going down the page. The different lines represent different objects, different actors in this interaction, and the arrows represent messages back and forth. So this is very good for understanding sequence of interactions. It's good for real-time specification. You can put real-time constraints on these things. We have several variations in which you can, they're better for procedural flow of control, where you can actually show the nested scope of control. And that's what these flow of control, focus of control diagrams show. The fat lines represent an area when an object is in procedural scope of control. And we've actually adopted the notation by the Siemens Group, the people with the Architecture Patterns book, called object message sequence charts, which is a very nice notation that we thought was pretty good. It's a variation on the message sequence charts. That's a CCITT standard, but we felt the Siemens people, they raised a number of objections to the standard message sequence charts not being very object-oriented, and we felt that their variation was actually quite good, and so we're using it. Now, doing things in time order is one way to do it, and that's a very good way of understanding what's happening and of doing things like real-time constraints. But it turns out it's not such a good way of actually designing procedures, and several of us have had this experience. I at one time, and Grady and our chief of development all had a situation where we, three separate things. We tried to design an algorithm, and we failed to do it using a sequence chart, but we were able to do it using this other form called a collaboration diagram. It's got the same information, but it's organized in a different way. On these diagrams, we organize the information around the actual objects and their relationships. So these diagrams show an object diagram with objects, links between objects that represent the different association links. And we show the flow of control as arrows flowing along these different links, because in an OO system, control has to flow along data link boundaries. And this allows you to see how control enters and re-enters objects, particularly in recursive and re-entrant situations. It makes complicated algorithms clear that would otherwise be very confusing. So we can represent nested flow of control with nested numbers. We got these from Fusion. We can represent parallel flow of control or concurrency. We can show creation of new objects and various temporary variables during the execution. Yes?
How do you handle polymorphism?
Question is, how do you handle polymorphism? Normally, in these things, you these are normally used to show various samples of execution. In a polymorphic case, you might actually want to draw more than one diagram representing different situations. So in fact, particularly since the flow of control might be very different in those situations, you would probably want to represent it with multiple diagrams.
Are you saying you'd like to represent that there is a capacity dimension where the method lives there? This is at the object level, remember?
Yes. But if you send a message to some other object, you don't know what class it is. So
Well, but an instance diagram, it has to be one thing or another. So the virtue of an instance diagram is it is a specific thing. And so to show more than one possibility, we need to superimpose more than one collaboration diagram. And in a sense, the overall behavior is the join of all of those possible diagrams. That's one way to handle it. I won't go through this, but this is a diagram that shows a factory control system with concurrent behavior and parallel objects, and we feel that we have sufficient notation to be able to represent parallel flow of control, forking, joining, and synchronization, and the difference between synchronous and asynchronous message passing. In a similar vein, when you get down to design time, you may wish to see the actual processes that are implementing concurrency on a computer system. We represent these as the traditional parallelograms. And we can actually represent objects as being in one process or another. An object has to live in some address space. So we represent it as being in the process whose address space it's in. And we can show the flow of control between objects. And that becomes a flow of control between processes. So when you see a flow of control between objects in different processes, that will have to be implemented with inter-process communication. If you see a flow of control within a given process, then that can be implemented in a single address space. So drawing a diagram of this form would allow you to balance the different bandwidth requirements, move things around so that your high bandwidth things are kept within a single process. Yes?
How we deal with threads? Because in threads, the objects don't have to be allocated.
I'm sorry, speak up.
In a thread, the objects don't have to be allocated to a single thread. They can be shared between threads.
Well, if at some level an object is owned by something. So it's in some address space, and that's what we're capturing is the address space. So in a traditional system, a process represents an address space. If you have a situation where they're all in one address space and threads are running in and out, you may not have a very well-defined system. I think it's going to be necessary for each of those objects to treat them as either having gatekeepers on them, so that each one is a concurrent object, and now it represents message passing between concurrent objects, or else I bet you're going to have a hard time getting the semantics right. So I think these thread-based systems can actually be trouble.
Are you asking about lightweight threads on heavyweight processes?
Yes.
Like threads in Windows?
Yes.
It's certainly the case that if you're talking about lightweight things, then the same object may be shared in the sense of a thread passing to the same object. And we have the same stereotypes as were in Booch for showing the different kinds of synchronization across the individual object. Is that what you're referring to?
Yeah.
So yes, threads.
It isn't shown here, is it?
No, no. This example, this is a web-based example here from Microsoft. We don't have a situation where there are multiple threads passing to the same object. But it is desirable, it is possible, it is common, as you described, for having overlapping threads across the same object. Correct. In fact, if you look closely in the previous diagram, you will see, I think, such an object is touched by multiple threads. Look at the A's and B's. I may be mistaken. Come up afterwards.
Right.
The other thing to keep in mind in the future is that probably in the future there'll be distributed threads in the process management program. You still have the idea of separate threads going through distributed objects.
I think, frankly, I think in the future this idea of threads separate from objects will vanish, actually, because it goes against the object-oriented paradigm, in which an object controls its own resources. So I actually think that concept will become less important in the future as computing power increases. As we get to a more concurrent-based implementation. But that's an arguable point that we could debate. Patterns, it's good to have them. You can think of them as a kind of interaction involving different classes playing different roles, and we represent them as a form of interaction that now involves both behavior and data. And at the high level, we can show the different classes that are participating in a pattern and the various roles that they play. Components, we mentioned, are pieces of software that exist as definable units at runtime, and it's desirable to see where they're located. We represent computers or nodes or resources as these three-dimensional shapes. We can locate components on various nodes, locate processes in various nodes, and show the dependencies between processes, components, databases, and objects on different nodes. So in this case, presumably this interface can be high bandwidth. These should be lower bandwidth unless we want to take a big performance hit. And finally, we can use the same sort of diagrams for showing the layout, the deployment of a system in terms of its runtime resources. So this would represent the layout of a system, a client-server system. Again, we can use this concept of stereotype to represent, in this case, how the communication channels between them are implemented. So another use for the stereotype concept to show a little more detail about the structure of a system. So at this point, I'm going to turn over to Ivar, who will finish up the talk, and when he's done, we'll take questions about the whole talk.
So now you have heard about the language constructs, all the things you can use when you make models, design your software. So it's time to put it together into a process, a way to work in developing your product. While developing a language like UML, we have had in mind a process all the time, a very generic process, a process that could apply in many different ways for many different types of applications, in many different different sizes of organizations, and that process was, of course, based on our own experience in how people use and develop software. We use the term process instead of talking about method, and primarily because we would like to describe something that can get a whole group of people to work together in developing a product. So they work together as a concerted effort and in producing a system. May I just give you a little bit analogy between method and process? You can think of a chemist who has, by using a method, a step-by-step procedure, put together substance after substance using a test tube and a Bunsen burner, and he has been able to produce some microgram of a new substance that really solves an important problem. Say it can help people with a fatal disease to survive. The director of marketing at this pharmaceutical company understands that this is really something good that the company can make a lot of money on. So he wants to develop, produce tons of this new substance. One way of doing it would be to use a 50-yard high Bunsen burner and a 200-yard long test tube, and in that way produce the substance in tons. But they wouldn't do that. What they would do is to use their chemical engineers to produce a process that would produce this substance in a line. And the same thing with software. To develop large-scale systems, we need to have a way that people can work together and together produce a result. Designing system, by the way, the term unified process, I would like to say is just a tentative term. It's something that we probably will replace with something better. but this is just for today and at these tutorials. Developing software means actually building models of a system, and you build models for many different purposes. You have all the stakeholders in the organization that participate in the development want to have a model of a system. Maybe there will be several models that we use, but there at least are models for everyone. The users want a model of a system, a model that represents the user interface and how to use the system. The analysts want a model, the designers want a model, the testers, the implementers, and you can go on like that to find several models of the system. So building software means building models, several models. And these models have to be related to one another in a consistent way. This process is also I said already, process-oriented. That means that it describes how different people work together and produce results that other people can use and go on till we have a product. It manages the system during its complete life cycle, which is from when you identify the need of a new system until the system is not anymore required, from bomb to tom. The process is risk-driven, which means that you do the activities that are of highest risk early up in the life cycle, and so you don't invest money in something that you have to throw away. It's cyclical. That means that the development, the life cycle, the total life cycle of a system is split into cycles. Every such cycle produces a new release or generation of a system. Every cycle is then split into phases, and every phase is consists of a number of iterations. One cycle, that means from one release of one generation of a system to the next generation of a system, passes through a number of phases. And in our case, we have 4 phases: inception, elaboration, construction, and transition. During the inception phase, the result will be a business case for the new product, which are the risks, what are the success factors, and what are the resources required to develop it, and it's also an idea of a new product. And the elaboration phase will result in a very good understanding of a system we're going to build. It's the architecture baseline is settled or decided upon, and also most of the use cases of a system are defined. And of course, a new plan, new costs, and new understanding of what the system what system is going to become and how much it will cost. And then we have a construction phase where we really build the system. That's where you finalize the architecture and you finalize you implement it, code it, test it, and during the transition phase, you deliver it to your customers. There is a beta release, which typically you have a beta release that some key customers use, and then based on that, you may do a number of new iterations until you have a product that you feel comfortably in releasing. So these are the 4 phases that that you pass through while developing a new release of a system. After this phase, you may take a new cycle with these 4 phases, and so on. And dependent on how far you are in the life cycle of a product, I mean, it's a first life cycle, you spend more work in the early phases in the first cycle than if you already have a product, then you spend more time in the later phases of work, in the construction phase. As Grady said, our process is use case driven. It's architecture-centric, and it's iterative and incremental. Apart from being a software engineering process, which means what I said earlier, it identifies all the different workers you need in the organization, and each one of them get their model and the artifacts. All these things are defined. This process is based on these three key factors. So earlier Grady asked you who has been using Booch, who has been using OMT, and who have been using Objectory or OSE. So may I ask you, how many of you have been using use cases? Wow. You too? So these three different factors will represent different dimensions of a process, and I will now describe one after the other and then relate them together. So now I'll talk about the use case driven part of it, and then I'll integrate that with the other aspects. Every iteration, that means going from one, when you do design, will pass through 3 process steps. And these are analyze, design, and test. Design and implement and test. So this is not a waterfall approach, because we are doing a lot of iteration. But you may actually describe the whole cycle of a system as consisting of a number of mini or micro waterfalls. Every such waterfall, every iteration will pass through these phases. During analysis, you clarify and capture, clarify, and validate the use cases. Design and implementation, you really realize the use case. You make sure that the system really implements these use cases. They will be there. And during testing, you verify that the use cases are fulfilled. And use cases bind these steps together. You will identify use cases early, and you'll make sure when you test the system that you really test use case by use case. Yes?
This would be a phase or an iteration? It's 3 steps.
This is one iteration, during one iteration. So I'll actually take a slide that is rather late in the package here. Yes, well, not the architecture. I took that, use that as well, but not right now. So during these phases, I'll come back to this later, but during these different phases, you see you do a number of iterations. So during elaboration, you may do 2, 3 iterations. And every such iteration will pass through all these activities. So you'll pass through, do analysis and design and implementation testing for every iteration. And if you do it in a good way, you can build later iterations can build on earlier without having to restructure. So you have to have a way of working, so you don't need to redo things that you have done earlier. Okay, yes, I need that soon. So I can pick it now.
Oh, just turn off the overhead because it's on.
Oh, so it's on. I don't need it now, so. I'll just give you an example. Here we have the automated teller machine. You have probably seen it many times already. So at least you know the example. What you do in the when you do use case model is you identify who are the users of the systems, what are systems are outside the system that you need to interact with. And then you identify the different ways that a user can use the system, an actor can use the system. And in this case, we identify 3 different ways of using the system. Then you describe it, and you may describe it using different techniques. You can use, typically, you should describe it using English, because that is really understandable by most stakeholders. But you could also use other techniques like state transition diagrams, interaction diagrams to do it. But what you do here, and that's the important thing, is actually you split the responsibility, identify the responsibilities of the system and the users of the system. So you identify what are the responsibilities of the actor and what are the responsibility of every use case in the system. And you define and describe these responsibilities. We had a slide earlier on how you describe, identify responsibilities, and then how you map them onto interacting objects. So once you have done that, we design it. And in this case, as you see, we are using stereotypes, and we are using let's say the collapsed form of them, where and in this case we have 3 different stereotypes. We have the interface stereotypes, cache stereotype, and cache. Sorry, we have the interface, we have the control objects or control classes, and we have the entity classes. These are the traditional notation that is used in OSC. Each use case here will correspond to an interaction class, and that is, has the notation of an ellipse with a dashed line. So for each use case, we identify an interaction in this case. And an interaction has a number of participants, and these are these classes that participate in an interaction. You can then use an interaction diagram, a collaboration diagram, or a sequence diagram to describe how instances of these classes, that's object, interact to perform a use case instance or a scenario. You do that for all 3 use cases, and the underlying model will be an object, a class diagram with classes and their associations, and you can trace every responsibility. The responsibility you have here in the use cases now are allocated to classes. So you split the responsibility over the classes here. Once you have done that, you can look at every class in the design and see how what use case it participates in, what use case it plays a role in. So this one participates in that use case, and this one participates in 3 different use cases. Yes?
Quick question. Do you still suggest, I know with Objectory we did views of participating objects for each use case. Is that still part of the process?
But we do, sorry, I did.
In the Objectory process, you had the views of the BOPOs, the views of participating objects. So I would show just the objects associated with a particular use case. Is that still?
I'm not sure I understand the question. Do you understand?
I think I heard it, which says, I don't even know the original Objectory process that much. In the continuing where we're doing the objectory process, you certainly would be allowed to render diagrams that the only purpose is to show the actors and their participants in it. Is that what you want to do?
Right.
Yes, certainly very legal because that is just a projection upon the underlying use case model.
Okay.
Short answer is yes.
Good, thank you, Gary.
You're welcome.
So once you have now done all these designed use case, this is of course a trivial example, because now we talk about a rather small system. We only need to talk about classes. We don't need to talk about packages. We are not talking about interface. We're not using the power of UML at all when we did it. We're not really talking about architecture in this example. So that is so this is really a trivial thing, but it shows one important thing, which what I wanted to show, is how you really go from use cases to design, and how you can trace every responsibility of a use case to an element in the design. And you can also look at an element like a class and see what use cases does it participate in. And that is extremely valuable, because if you want to change something, you have a way and mechanism to follow these changes throughout the development work. So once you now have designed it, and implementation is rather straightforward, because you have identified the classes, and you also have a specification of every class when you have done this kind of designed every interaction. So now implementation is taking this specification and turn it into code, efficient code. Testing you do in design and implementation, you unit test your software, so you unit test every class in a traditional way. Integration testing is done by testing use cases, use case by use case. Every one of you who's developed software in the past have also tested it. And the way you do testing is basically use case testing. You test use case after use case. The use case may correspond to many different test cases, because you can follow many different paths through use case. So good thing is, once you have done the analysis and identified all the use cases and specified them, then you can start several activities. You can start the design and implementation, but you can also start planning the testing work. So you can, when you have identified the use cases and described them, you can start planning the work on testing. When you have done the whole design and using interaction diagrams of different kinds, you can follow every path through the interaction diagram. From these you can generate test cases mechanically. And what remains to be done is for you to put in the values of the different data that you really want to test. So you have tested value ranges. So as you see, use cases run through the whole, these through steps, which correspond to an iteration. You start up and identify for every use case. Every use case will be the responsibility of a person, analyst. So you put, for every use case you have an analyst responsible for it. An analyst may be responsible for more than one use case, but that is quite normal. When you go to design, you have one designer, use case designer, for every use case, every interaction or set of interactions. When you go to testing, you have one person responsible for doing testing each use case. And then, of course, during implementation and design implementation, you have people who do the design of the software. They design the classes, they design the packages. You have the architect who is responsible for the overall architecture of a system. Yes?
How's the fault tolerance of the testing is
How-
generated?
Excuse me?
How's the fault tolerance, the system that
for the fault tolerance testing. Your use cases are primarily for the test of the logical
Functional.
function
Yes.
behavior. But where's the fault tolerance part? Prevent user to do something silly.
So-
Prevent user to do something not permitted.
Yes. So apart from that is, so what use cases help you is to identify the test cases, and then and if it, because in the old days, so to speak, then typically people did the design, and then the testers had to figure out what are the things I have to test. So that is the help you get here, and you also can generate these paths you want to test. However, the rest of the work remains, and it hasn't changed. It's still there. You need to do the, as you have suggested, test. You need to do negative testing. You need to do testing that means that you have many instances of the same use case going on concurrently. So you have to do load testing and things like that. That hasn't changed, but it's based on use cases. Now the other component is architecture-centric. And that is, architecture is key to design a system that you can manage over its lifetime. Without having a good architecture, the costs of maintaining the system you have developed for releases to come will make it may be so enormous so that you will have to throw it out and redesign the whole system. So architecture is absolutely key, and the idea is that you start by finding the architecture as early as possible. You do that during the elaboration phase, and that means that early iterations of a system should focus on finding the architecture. So what is architecture? Well, architecture is an aspect of design. So what Grady earlier talked about, these different views.
Turn off the overhead.
These different views of a system: logical view, a component view, concurrency view, deployment view. They are all different aspects of a total design of a system. So a system will be modeled from all these views, dependent on the kind of system you're developing. But these are the views that we need to model to get the system that fulfills all the requirements. Now, architecture is that part of these views that are the most significant parts of them. So, and so it's the most interesting aspects of the system, the views that represent the architecture. Architecture is defined. Many people have tried to define what is architecture, and there is a work group in IEEE as work group that has defined architecture as the highest level concept of a system in its environment. It's very hard to give a precise definition of what an architecture is. So it's the highest level of these different views that are the most important, that represent the architecture of a system. Let's see. So we have given it this definition, and that is, well, you shouldn't treat this as a definition. It's just a proposal for a way to view what is architecture. It's a structure of components interconnected through interfaces. Components are composed of successively smaller components and interfaces and interacting components of the system's behavior. That is the interactions. An example of an architecture is layered, the layered architecture. And in this architecture, you have the bottom layers that are the platform, the system platform in terms of operating system, database management systems, and so on. Then you have a layer that contains generic components like graphical user interface builders, interfaces to database management systems that are generic components that you probably may procure from outside. You don't need to design them yourself. On top of these things, you have the software that actually is particular for your application. A large organization, for instance, a banking system or a system in telecommunication, is typically designed should typically be designed in this way. And one layer here contains the domain-specific components that are classes, packages, frameworks, patterns that are reusable over many different applications in the same domain. And on top of them, we have a different application system. So all these things, these boxes here represent different systems, and could all be modeled using UML as with use cases and analysis model, design model, implementation view model, and testing, and so on. These 4 different views you have for every component here, every system here. When you to really succeed in managing these kind of complex system, you need to have not only the architecture like this one, but also an organization where every system here has its own processes and an organization that maps this architecture. So typically, in designing a system like one I just described, the architecture I just described, you have an organization that maps that architecture. And you have a process, for instance, for taking care of the overall architecture. The responsibility of that process is to identify the different systems of the organization, system of the whole architecture, and the interfaces between the different systems. Then you have one process for designing an application system, another process for designing a component system. And you may have a process for procuring components from outside vendors. So the way you develop these things is that during these different phases, the first phase, in Inception phase, you identify some use cases, and based on these use cases, you come up with a skeleton of an architecture. So you get an idea what the product is. You make a business case for the product. You can get an estimation of the costs. When you come to the later on in the elaboration phase, you make a number of architectural prototypes, and before you leave the elaboration phase, you have designed the architecture of the system. Finding the architecture of a system is based on a number of sources. We identify the highest risks. What are the highest risks in this project? Risks are, for instance, using a new database management system, or using a new technology, a new language. You haven't used it before. You're developing a distributed architecture on a platform you don't know before. These are important things that you look upon when you design the architecture and when you do these early phases of a work. Other important things that will drive the architecture are the use cases of a system. To find the architecture of a system, you need basically 20% of the use cases, just to give you a rough number, 20% of the use case of a system, and you need only 20% of the scenarios of these use cases. So typically, what that means is that you only need, let's say, 20 times 20, it's 4% of a total functional mass to come up with the architecture of a system. And the architecture, that means, as I said earlier, it's these four different views that you have to specify. You specify the logical view, which contains the classes, subsystems, interfaces, and so on. You specify the concurrency view, the deployment view, and the component view. You design it. And you do that by using use cases to identify, to capture them all and to get the architecture right. And for that you need, as I said, 20% of use cases and 20% of the scenarios of each use case, which is only 4% of the total mass. It's really something you can do early up. When you do that, you don't only design it, but you actually code it too. So you code these 4 or 5% of the use cases and implement it and test it and run it. And now you have something to show your people, something that you can show your users, and you can improve. If you have done it right, if you have identified the right use cases up front, then you don't need to restructure it. You can then take the next iteration, you can build on the architecture you had, and you don't need to restructure it. So when you develop, you will pass through a number of iterations. Every such iteration consists of these 3 steps. And the use cases will drive the development, particularly for the higher layers in the architecture. The lower layers of the architecture will be dependent on other factors, non-functional requirements. But the higher layers will be dependent on the functions and that are use cases. During these 4 phases, you spend the time you spend on different activities varies. You do planning through all the phases. Every iteration means that you also need to plan the next iteration. And of course, you do more work in the early phases, in inception phase, on planning, because when you plan the whole project. Analysis, you do most of the analysis during inception and elaboration. Architecture, most of it will be done during elaboration. And so on design, now you do during elaboration some design, particularly that has to do with architecture, but also most of it will do during construction. Implementation, you will implement the architecture and the design that you come up with in the early phases. So you start doing coding and implementation early, but most of it will be done during the construction phase. So it's interesting to see how you actually move during these 4 phases. During all 4 phases, you actually do basically all of the activities. But you do more in some phases than you do in others. And when you go on, the next iteration, then it will look different. The next release of a system, next generation, you will spend less work in elaboration, probably, and more work under the construction phase. Yes?
Just estimate, how long would you say for a moderate-sized project it would take me to get through one cycle? A number of months, a number of years?
For one cycle?
One cycle.
That means one release of a system?
Right.
It varies very much. But I mean,
Can I put in a shameless plug? Go read Object Solutions and it gives you such a rule of thumb. Tell me the life cycle you have. What's the average life cycle?
that's a sales pitch.
Yeah, it's a stage pitch. Tell me average, how long is your life cycle?
Well, this is what we're dealing with. We look for like a 9 month, and they say do it in 3.
Well,
So we try and do it in 3, and then they
send us
say
your
do it-
resume.
Yeah, right.
Let's suppose it's 9 months. Sometimes you have to tell management that a succession of lies has to be owned up to eventually.
Well, I'm
And
wondering.
let's assume it's 9 months.
Okay, is
Take-
that even reasonable? That's all
I don't know what your project is, so it's hard to say.
Okay.
I know of life cycles that are a few months.
Say 20 major use cases.
20.
Okay, so I think if you really want to, that's impossible to answer your question, basically.
Okay.
So the thing we would like to say here is, if you have a very good architecture, you can reduce the time, and you will do that. And particularly, architecture is extremely important to get reuse, for instance. And one of the key instruments to really get shorten the cycle in producing new releases is to be able to reuse. And the less you need to redesign, the more you can use, the shorter the cycle can be. That's more generic. Yes, please.
Where do you put requirements development in there?
So requirements, there are different. These are different approaches for doing requirements development. In this particular case, we are describing a situation where you actually are developing requirements as you develop a product. So, but typically, in front of all these things, we would like to say that, depending on what kind of application you're doing, but suppose you're designing a banking application or finance, then we would like you to do a business model to start with, so you really know what business you are going to support. Otherwise, you have no clue what the software you should develop. You can just guess. So, and then there are other kinds of systems where basically requirements are outside of these activities. Well, I also would like to say there are lots of requirements that you actually find while you do the work. I mean, for instance, in the old time, you specify the requirements that I've seen specifications that have been rather fat, and people try to sit and specify things that they actually shouldn't deal with because they didn't really know what the users needed. So what typically happens between 2 iterations is that you evaluate the product, and we evaluate the user interface. You may evaluate if the product really is doing what the business requires, and that may lead to changes in requirement. So, yes. Another question?
How, as you iterate through that, how do you force the user to sign off on a use case, or sign off to the point where you can finish it and go?
Well, I think this is the end of the elaboration phase. When you're at the end of the elaboration phase, you should be able to make a contract with a contractor and agree on the rest of the work. So the Rational has developed a number of business cases, how you actually can, dependent on the situation, how you actually can make a deal that both parties will be happy with. And it depends on the kind of product, and it's done different dependent on where you are in the life cycle. Yes?
You answered the question that requirements engineering should be outside of this life cycle. Does this mean that this life cycle is not complete, or what's actually missing?
So is something missing here?
Yes, your answer was that requirements engineering is...
Well, it will be added in front of it. So what we are trying to do now is to describe what it means to develop a cycle where you have had a good understanding for the requirements ahead of it. Now, if you want to develop a business, for instance, you need to do, you need to, in the early phases, do, in this inception phase, you actually, doing analysis, you put, you also include this kind of modeling that has to do with requirements, yes.
Can I suggest that we take the process questions, maybe we have a process group out here after 5 and address some of those. This is not so much to be on process, but we have a whole set of process things we can talk to you about, some of the work that Ivar and Philippe and Walker are doing, and we can maybe address those more in context. So I don't want to shut you off, but maybe we can get the process.
Yeah, I think if we are going to be able to answer other questions as well. So you see how you spend more work dependent on where you are in the life cycle, and also where you, in which iteration you are during a cycle, you spend more or less work. The unified modeling language and the unified process, they are two parts of a whole. You cannot, we wouldn't be able to design the language without having a process in mind. And on the other hand, you couldn't design a process without having a language in mind. So these two things are related to one another. Regarding the language, we can see today that we get convergence between basically most methodologies. We have a convergence going on, and we believe that we'll get the standard in the near future in language. That means that the interest, a lot of the interest, will move over to a process, and how to really use this to develop products. We believe that what we can do today is to identify a process framework, a framework that can be specialized to basically any application. We did that with the old Objectory product and the new Objectory product that actually incorporates a lot of work by Grady and Jim, but also by many other people inside Rational with a lot of experience in process. Is something that you can specialize for basically any kind of project. So one of the things we can see is that there will be specializations of this process that can fit many existing organizations' needs, but it's through specialization. So now I'll just tell you a little about where we are. We have now, late this year, we'll produce this 1.0 of UML. And we work on these collaterals right now. It will contain a meta model, and it will contain a complete meta model of a language. And that will be submitted to OMT in early 1997. Actually, it's the 7th of January. And during the first half of 1997, we'll get feedback on that and work with OMT on getting a standard. I think we have seen in the past a fragmentation, a lot of different methods being out there, and we are now seeing a unification. Unification between methodologists and also over different areas, not only software but also business, engineering, and systems engineering in general. That will result in standardization. We will get a standard for for modeling these kinds of systems. And I think that is a need. If we really are going to become a mature industry, software industry, we need to get the standard as a platform to do that.
Well, then, thank you, and
See you all at Great America.
please,
Thank you.
please